Hello students, today I'll start the topic measurement of standard reduction potential of zinc. Now we all know that standard hydrogen electrode is the reference electrode, and by connecting any other electrode to this standard hydrogen electrode we can find the electrode potential of any electrode. For example, here in your syllabus it is the measurement of standard reduction potential of zinc and copper is there. Now I am starting with measurement of standard reduction potential of zinc, that is E naught Zn2 plus 2 Zn. We know that in previous video I had very clearly explained that when it is the measurement of EMF, always the cell potential of the cell is represented in the form of reduction potential and reduction reaction. Now, the entire setup for measuring the standard reduction potential of zinc is in front of you. That is, the left half cell is composed of zinc rod in zinc sulfate solution, that is 1 molar. The right half cell is composed of hydrogen electrode with 1 m HCl. Now, this hydrogen gas is bubbled at 1 atmosphere pressure and 298 Kelvin. So, when this entire cell circuit is completed, this galvanometer shows a deflection of 0.76 volt. I am repeating, when the entire setup is completed, the galvanometer is showing a deflection of 0.76 volt. This is the experimental value. The cell is represented as zinc 2 Zn2 plus 1 molar. Then salt bridge is in between, hydrogen plus 2 hydrogen gas at 1 atmosphere pressure, and it is platinum electrode. So this is representing the anode area, this is representing the cathode area. Anode and cathode are separated by salt bridge. Now, the EMF or the standard reduction or EMF of the cell, E naught cell at standard conditions equals to, we know that E naught cathode minus E naught anode. Now here, who is cathode? Cathode is hydrogen electrode and anode is zinc electrode as represented by the diagram. And we know that after completing the cell circuit, here the deflection is showing 0.76 volt. This implies 0.76 volt equals to E naught. Cathode is represented by hydrogen, that is we can represent 2H plus 2H2 minus E naught Zn2 plus 2 Zn. This presentation is highly essential. Students, you just observe, this presentation is highly essential. How to represent cathode and anodic part. That this implies 0.76 volt equals to, we know that the cell potential of standard hydrogen electrode is 0 minus E naught Zn2 plus 2 Zn. I hope you are getting. This implies E naught Zn2 plus 2 Zn is found to be minus 0.76 volt. So, this is one part of the question solved. That is how to measure the standard reduction potential of zinc using SHE or NHE. Here I am repeating the entire concept within a NOR cell. That means NHE or standard hydrogen electrode is acting as cathode and hydrogen, that is zinc electrode, is acting as anode here. The two cells, half cells, are separated by, or you can say interconnected by a salt bridge. This is the galvanometer which shows the deflection of current. The cell is represented by this, and E naught cell equals to E naught cathode minus E naught anode. Cathode is represented by hydrogen electrode, anode is represented by zinc electrode. And after all sort of calculations, it is coming E naught Zn2 plus 2 Zn is coming minus 0.76 volt. Next, I am just going to explain you how to find the electrode potential of copper. As per your syllabus, measurement of standard reduction potential of copper, that is E naught copper 2 plus 2 copper. And for this, the entire setup is in front of you. That is, standard hydrogen electrode is taken in the left half cell and copper in copper sulfate solution of 1 molar is taken as the right half cell. The two are interconnected by a salt bridge, that is inverted U-shaped tube, that is salt bridge. Now galvanometer is also placed here. This is showing deflection of current. The cell is represented as hydrogen, that is H2 gas, 1 atmosphere, okay, bar H plus 1 atmosphere, that is 1 molar, then salt bridge copper 2 plus 1 molar, then separated by copper solid. Okay, this part is representing anode, this part is representing cathode. This anode and cathode are separated by salt bridge. This is the presentation of the cell. Now accordingly, E naught cell of this particular cell equals to the same E naught cathode minus E naught anode. Getting? This implies, again we know that when the entire cell circuit is complete, the galvanometer is showing a deflection of 0.34 volt. That is 0.34 volt equals to E naught. Now what is cathodic presentation? Cathodic presentation equals to Cu plus 2 to Cu minus anodic presentation is E naught 2H plus 2 H2. I hope you are observing that when EMF calculation is done, or E cell or E naught cell calculation is done, the presentation of cathodic or anodic are presented in the form of, that is, reduction reaction. Just observe, here it is in the form of reduction, here also it is in the form of reduction. Okay, because this is as per modern IUPAC system. This implies 0.34 volt equals to E naught copper 2 plus 2 copper minus this entire, we know that this is 0 volt. Okay, this implies E naught copper 2 plus 2 copper is found to be plus 0.34 volt. This is what your calculation done. Now one thing or one clue point let me cite in front of you. Any electrode whose reduction potential, standard reduction potential is to be determined with reference to standard hydrogen electrode or normal hydrogen electrode can be positive or negative. There is a rule. The rule I am citing before you, that is the electrode in which reduction reaction takes place. I am repeating, the electrode in which reduction reaction is taking place with reference to SHE or NHE is assigning a plus value of reduction potential, and the electrode in which oxidation reaction takes place with reference to NHE or SHE is assigning a negative value of reduction potential. I am repeating, the electrode at which reduction reaction takes place with reference to NHE is assigning a plus value of reduction potential, and the electrode at which oxidation reaction takes place with reference to NHE or SHE is assigning a negative reduction potential value. This is what your syllabus taking to measurement of standard reduction potential Zinc as well as copper over. Now the very next area I am going with reference to a syllabus, that is Electrochemical Series. This is what in 10th standard you have already gone through in 10th standard. That is what is known as Electrochemical Series. Students, you know that any electrode we can find the standard reduction potential by connecting with SHE or NHE. Similarly, this entire electrochemical series is composed of many reduction potential values as you are seeing in this picture. That is, this electrochemical series is now composed of, or before going to electrochemical series, let me give the definition part of it. It is the series which is representing the decreasing order of reduction potential values. That is, I am repeating, suppose it starts from 2.87, now it is going and it is decreasing with reference to the values. Now here it is 0.00, means now hydrogen electrode is in between, and now it is assigning negative values till it is going to the least, that is from least negative to most negative value. So repeating this area, electrochemical series is the arrangement of electrode potential, that is necessarily reduction potentials with reference to the negative, that is with reference to the decreasing tendency. Okay, because all these electrodes are now got the values of reduction potential by connecting individually with SHE or NHE, and this is what the entire electrochemical series. But here let me be very clear that you need not to remember this entire electrochemical series. The values in numerical area it will be given to you. Only you need to remember what are the utility of electrochemical series. I am repeating this, that is electrochemical series is the series of reduction potential values in which, just see, hydrogen is in the center. Hydrogen is in the center. Upon hydrogen, electrode potentials are higher values are on the top and lower values are on the bottom. Now I am going to the utility area of electrochemical series. Now, taking to this entire electrochemical series, we can say that there are various application areas of electrochemical series. That means the electrochemical series helps in determining anode and cathode of any electrochemical cell. For example, if it is now taking to, let me cite, if the question is taking to what is EMF of the cell. What is EMF of the cell, in which I am writing the question for you. First application is how to calculate EMF of a cell. What is EMF of the cell in which the following reaction takes place. Zinc 2 plus 2 electron minus is giving zinc. Here given E naught Zn 2 plus 2 Zn equals to minus 0.76 volt. Ag plus 1 electron minus is giving Ag. E naught Ag plus to Ag given the value 0.79 volt. Here it is plus. Okay. Now, as from electrochemical cell or electrochemical series, we have observed that this zinc is getting the value of minus 0.76, silver is getting 0.79 volt. That means from these two we can be very clear that which one can act as cathode and which one can act as anode. Okay, and just tell me which one can be cathode. The electrode having higher reduction potential. So among these two, which one is higher? Definitely 0.79 volt is higher. Therefore, let me write EMF, that is EMF equals to E naught shell equals to E naught R, that is right, RIGHT minus E naught left. This equals to, who is representing right cathodic here? E naught Ag plus 2 Ag minus E naught Zn 2 plus 2 Zn. This equals to 0.79 minus of minus 0.76 volt. This implies E naught cell or EMF of the cell equals to 0.79 volt plus 0.76 volt. Okay, and definitely this is coming to be a positive value. That means EMF of the cell is coming to be a positive value. This is what the first application. That means how to calculate EMF of a cell by taking anodic and cathodic. So this is first application. Let me give the second application of electrochemical series. You can say in a reverse way that this electrochemical series predicts us how to distinguish between anode and cathode. That means the electrode having higher reduction potential act as cathode and the electrode having lower reduction potential act as anode. Suppose the value is, let me explain you few questions here. Suppose the anodic and cathodic reaction is to be chosen from plus and minus value. Suppose it is 0.79 0.79 volt and 0.34 volt. So automatically from this, who is bigger? 0.79 volt. So this will act as cathode and this will act as anode. So this is what when the values are given or the electrode potential is given in plus and plus. Now I am going to the next. Suppose it is 0.79 volt and minus 0.34 volt. I am just explaining arbitrarily. It is not the exact value of any electrode. Okay. So this is obviously this is acting as cathode and this is acting as anode. Third, when it is between two negatives, let it be minus 0.79 volt and minus 0.34 volt. Now you tell me who is bigger here with reference to standard reduction potential. The rule is that among these two, which electrode is going more towards 0 is higher value. I am repeating, among these two value, which one is going more towards 0? Which one is going more towards 0? I hope this one is going more towards 0. So this will act as cathode and this will act as anode. So this is what I am repeating. When this values are given or anode and cathode are given in plus and plus value, definitely it is very easy to distinguish which can act as cathode and which can act as anode. But when it is plus and minus, then also it is very easy. But when it is taking to minus and minus, take it a point that from these two you go to the number line from of your area of your childhood days of mathematics. That means the value which is going more towards 0 is more higher value with reference to standard reduction potential. Therefore, among this minus 0.79 volt and minus 0.34 volt, definitely minus 0.34 volt is more towards 0. That means it is higher value with reference to standard reduction potential. Okay, with reference to positive area, positive value. So this will act as cathode and this will act as anode. Accordingly, we can calculate the EMF of the cell or we can distinguish anode and cathode. So this is what the second application also over. Now let me give you the third application of it. Suppose any reactivity of any element can be also distinguished or determined with reference to electrochemical series. Now you see these are the positive values are coming till 0. Then negative starts and negative is going or it is extending to the maximum. We know that any element having negative electrode potential, okay, negative value of electrode potential means negative value of standard reduction potential is considered as more active. I am repeating, any element which is assigning more oxidation potential. These are negative values means these are oxidation potentials. Okay, and these positive values means these are reduction potentials. So any electrode which are having negative values of reduction potential means they are higher oxidation potentials. So more oxidation potential or negative value means these elements are more reactive as compared to these elements. Now also it's a fact that a more reactive element can displace hydrogen from mineral acid. For example, let me cite you. Here it is zinc. Just observe. Here it is zinc. Zinc is Zn2 plus to zinc. The reduction reaction is Zn2 plus 2 electron minus is giving zinc. Is assigning minus 0.76. That means this zinc is more reactive and it can displace hydrogen from acid, mineral acid. Again, here if you take the reactivity or the power of reactivity between two elements, this is minus 0.76 and this is, suppose we will be taking ferric minus 0.04 volt. So among this iron, that is ferric to iron, okay, this is taking to iron and zinc. Who is more reactive? So definitely zinc is more reactive. That means zinc can displace iron from its solution, which we have already gone through in 10th standard. I am just repeating that. Zinc is, if you compare the reactiveness between zinc and iron, so zinc is better in displacing iron from its solution. Whereas if you take copper, having 0.34 volt, it cannot displace iron from its solution. That is what the third application of electrochemical series. That means electrochemical series predicts whether an element or electrode is reactive or not. Reactive means it can displace hydrogen from mineral acid, or it can displace any other element from its salt solution. Third part is it also predicts the reactivity of or the feasibility of any reaction, any redox reaction. I'll cite that. Let me cite that in a very clear-cut way.